Hey everyone.
Hi.
Thanks for joining this session on not Marcus's one on HTTP 3. We are going to be attacking the problem a layer down here, talking more specifically about QUIC and how we implemented a QUIC stack in VPP, the vector packet processor. So I'm Elois, I'm here with Nathan. We are both from Cisco. And Nathan will now start introducing QUIC.
Right. Okay. So first, what is QUIC? I'm not sure everybody's familiar with it. So it's we've been dealing with UDP and TCP for a while, and QUIC is supposed to be the successor of TCP. Some might call it TCP2, but not everyone does agree. But more seriously, how does it play with the stack that we have for now? So we've been having HTTP living on top of TLS when it's HTTPS, TCP, and the IP layer, or UDP. And the idea of a new protocol is to replace the TCP plus TLS layer by a new layer called QUIC, which is going to be hopefully coded in user space and have some nice feature. The purpose of it is also to switch from HTTP 1, 2 to HTTP 3 to introduce new feature to address a few of the concerns that we had with HTTP. So some nice properties it has is that it provides encryption by default, retaking the TLS 1.3 handshake. It's designed so that it prevents ossification in the network. So most of the packet, pretty much every bit of it is encrypted and encoded, so that the middle boxes cannot take decisions on the packet path and do things with it. There is built-in multiplexing because it's a very common application requirement, and that's some issue that we had with HTTP. It provides independent streams in each connection to address this multiplexing. Addresses head-of-line blocking. That was an issue with HTTP1 that was supposed to be addressed by HTTP2. And supports some kind of stream prioritization. So basically, it adds a bunch of new feature to the old transport layer. Also, a very nice thing is that it supports mobility. So when you establish a connection between two peers and a 5-tuple, you get a connection ID that you're then able to move across IPs and ports. And that should be fairly seamless for the application. So just to recap how things works, when a server and client want to talk, they can open connections, and in every connection they can open different streams, and each stream should be fairly independent from each other. To recap a bit pros and cons, so the cool thing about it is that it runs on UDP. So it can be implemented out of the kernel and can evolve quite fast, which is a nice thing because it's not yet an IETF standard, which gets into cons. Again, it addresses head-of-line blocking, provides mobility, and provides encryption by default, which is nice when we try to move to HTTPS. But on the con sides, it has some complexity that we've tried to address by implementing it. And for now, we don't have a very standardized northbound API, something that we want to address in this talk. So
let's now take a closer look at the code. The building blocks that we had for this project, we basically need something that a client application can consume. It provides an API that's hopefully familiar and easy to use. We need something that can send and receive packets, UDP packets preferably, and we need a QUIC implementation. We are not re-implementing QUIC in this project. We will be using a library that does that. So what we chose, so for the QUIC implementation, we used Quickly, which is developed by Fastly, which makes very few assumptions about how the memory is managed, where the packets come from, and is very modular. So this was very pleasant to use. For the packet processing, we use FDIO VPP, which is the project we are working on at Cisco, which comes with fast layer 234 networking and a pluggable session system, and also a client library that exposes the session layer for applications. So not all of you may know what VPP is. So very quickly, it's an open source, fast user space networking data plane. It's very much focused on performance. It uses vector instructions. We are very careful about cache efficiency in VPP. It is extensible. You can relatively simply write plugins for VPP. It comes with all you would expect from a software data plane, layer 2, layer 3, tunneling protocols, etc. And more importantly for today, what we call the host stack, which is a layer 4 protocols implementation. So this is going to be our platform for the QUIC stack. So more precisely, the VPP host stack is a generic session layer that exposes layer 4 protocols. The API is socket-like, meaning that it tries to reproduce the Berkeley sockets API, just to make it easier to consume for external applications. Even though the internal API is more efficient, in particular, it doesn't involve required copies to pass data around. Instead, we are using FIFOs, where applications can write data and the protocols can consume it, and inversely. So it does have an internal API that we can consume in plugins. The external API is exposed through a message queue, but it's very much the same API, and it's designed for high performance. So we can almost saturate a 40 gig link with one TCP flow, almost because congestion control is hard, and we can fully saturate a 40 gig link with one UDP flow. And it's built to scale linearly with a number of threads, so different sessions are always assigned to a thread, and they are completely independent from each other. So for a more visual overview of the host stack, we see the session layer in the middle here, which exposes a standardized API over layer 4 protocols, the specific protocol implementation below it, and then the layer 2 and 3 networking, which we won't focus on too much today. And this session layer is consumable either internally with plugins that live inside the VPP process, or externally with control events going through the message queue. Control events which include connection events like new connection, connection closed, data available on one of the FIFOs, etc., etc. So now for what are the requirements for an application that uses QUIC? As Nathan said, QUIC is a bit more complicated than your regular layer 4 protocol because it includes multiplexing. So that means that we have a new type of object that we don't really have in a traditional socket API, which is the connections. So a QUIC app needs to manage listeners, connections, which are basically just shells for streams and which take care of encryption, and streams themselves where we can send and receive data. So one of the first challenges we had is that we needed to integrate into a socket-like API, and that didn't really fully map to QUIC, not entirely. So what we did was, first for the listener, nothing changes. You just listen on the UDP port, and that's really what you always do. Now, things get trickier when you connect. When the client connects, it will connect to an endpoint IP port, and it will receive a new connection, a connection object, conceptually. The server will accept that connection and also receive a connection object. And with that connection object, clients can know, well, both the client and the server can now open streams. So in order to open a stream, we modified a bit the connect call to be able to pass a reference to a connection. And both the client and the server also need to accept streams on the client. So like you would accept on a listener, you can accept on a connection. This is a bit weird, but we think this allows to closely map the QUIC concepts to what you would expect from a socket API. So the connection sockets are only used to manage streams, accept and connect them. They cannot send and receive data. For that, you need actual streams. Streams can also be unidirectional or bidirectional on QUIC, meaning that you won't be able to send data on certain streams you accept, because unidirectional streams are always opened by the peer who sends data on them, but this doesn't change as much. So once you have a stream, you can just call send and receive on the stream. Now back to Nathan for how we actually build that in VPP.
Yeah. So now that we have the structure and the sockets that we want to expose, the idea is to leverage VPP because it's the project we work in to add this QUIC stack. So coming back to this session layer that lives on top of UDP that we're going to use, the first thing that we did is actually build a second layer. So replicate that session layer and add a QUIC protocol on top of the UDP and session layer. So basically, we build a plugin inside of VPP that acts as an internal application and that consumes the session layer as would a normal UDP listener do. And then those sessions can be exposed to an external application through the message queue and control events. So we replicate the FIFOs, we replicate the data structure, but it's at first for the sake of easiness and pluggability inside VPP. Zooming a bit inside this QUIC brick, what we are going to play with is a northbound interface that are going to need to take from the buffers the FIFOs that are exposed to the client application, pass this data, this stream data to the QUIC library from Fastly that we are using internally. The PicoCLS brick inside of it is the crypto backend. So as we mentioned earlier, quickly it's very nice because it exposes a lot of callbacks and pluggable interfaces that allows to modify and change things. So that's the crypto API we're going to talk about later. And then it provides also callbacks softbound to copies the encrypted buffer to the UDP sessions, UDP buffers in VPP that are then forwarded to the wire. This model is quite interesting because it provides three different consumption models from a client application. You either can write an external app that's independent using the socket API we described. You can also write an internal app because VPP provides a large range of plugins that integrates directly with the internal API provided as standard C functions inside of the code base. But you can also integrate directly with the interface provided by QUIC. So that allows us to be very modular and to adapt to different use cases. For example, if you want to build, let's say, a forwarder or a VPN termination point, you're gonna maybe write an internal application that's just gonna do the forwarding and the mapping between, let's say, TCP and QUIC. But if you want to adapt iPerf to use a fake type of QUIC, you're gonna maybe stick with an external application, going with regular sockets. So like those sockets we defined. But you can also adapt if you have an application using the QUIC library, using directly those callbacks. Now, if we follow a packet coming in, what's going to happen to dive a bit more inside the architecture? What happens is that the packet gets copied from the wire, gets copied inside the UDP buffer RX54. It triggers a session event that gets called by QUIC. Then the packets is initially decoded because of the obfuscation, everything is encrypted. Then we match it against a connection, match it against a stream. We decrypt the packets. We do the crypto processing, and then deliver it either to directly to QUIC or to the QUIC stream buffer that's going to act as the application buffer. And then this decrypted payload can be consumed either by an internal client or an external client via the message queue. So this brings a couple of issues. What happens if, as those FIFOs are fixed size, what happens if we exceed the amount of data we are able to store? So that doesn't matter that much on the UDP session part because that buffer is merely temporally. We don't really store data there. It's just to pass data from the wire to the packet decoding node. But that stream FIFO can make things break. And that's due to the nature of the QUIC protocol. The issue is that before the packet is decrypted, we have no way to know which streams is going to contain data for. In QUIC, data can be coalesced between packets and can also control frames. So, and everything is encrypted to prevent ossifications. And once the packet is decrypted, quickly the library does not allow us to drop the packet, because you would have to revert all the control frame that you processed earlier. So if you drop the data, the data will never be retransmitted, which is quite sad for congestion for that type of protocol. But fortunately, we have a connection parameter called max stream data that limits communicates between the peers the maximum amount of data that you can send an act on a stream, and that allows us to control that transaction, setting it to the maximum FIFO size. And so that proves a bit the maturity of QUIC, because it has several other connection level settings in that sense to control the maximum number of streams, the maximum number of unidirectional streams, and the total amount of unact data for the connection. That allows us to handle those kinds of tricky cases that the implementation sets on the way. So after RX, then we want to, after having received the packets, we now want TX1.
And so you probably noticed the TX path is really similar to the RX path. It's just the same graph, but in the opposite direction, basically. So the data can come either from external apps or internal apps, in which case it will be pushed into the QUIC stream session TX FIFO. Which will trigger an event which will call quickly, or it can come from a Quickly app using directly Quickly and telling it to generate new packets and send the data. So just one thing to note here is that the FIFOs are by stream, but Quickly generates packets for the entire connection. So you may have data pushed from different streams. You just need to call Quickly once to generate packets for the entire connection, because Quickly will it will call its internal scheduler to select data from the different streams according to their priority, etc., and generate packets from them, encrypt them, put them into the UDP session TX FIFO, where they will be sent on their way by VPP. There are also a couple issues on the TX path that we need to take care of. In particular, the back pressure, so how we make sure we don't encrypt packets that we actually don't have space for in the UDP TX FIFO to send them, which would be a bit sad, a big waste of cycles, or how the apps know that they need to wait before sending more data. So fortunately, on the lower side, it's pretty simple for UDP, because when we tell Quickly to send packets, we can actually tell it to send a certain amount of packets. And based on the available space in the UDP FIFO and the MTU, we can just limit the amount of packets generated to make sure they always fit. And then from the application side, the back pressure just comes from the FIFOs, where Quickly will stop taking data from the stream FIFOs, and the applications need to check the space available in the FIFOs. And they will see that they don't have space left to send data, and they will naturally stop sending data. Another question is also when the applications can know that Quickly has sent more packets and they are not able to send more data. There is a host tag feature to actually trigger notifications to an application when space becomes available in one of its FIFOs. So that works pretty well. Another important thing that we have only touched a bit for now is the threading model. So first, generally VPP runs either with one thread or one main thread plus several worker threads. And as we said earlier, sessions are always pinned to one thread, one specific thread. The thing is, we don't get to choose which thread the session gets pinned on. That depends on RSS. meaning that the NIC will receive a packet, it will assign it to a queue depending on its 5-tuple hash, and VPP will get it on the specific thread which manages that queue. That's a bit of a problem for UDP, because when we open a connection, we'll first send a packet in one thread, and the reply may come to another thread. We can't know in advance. So in order to handle that, the host stack has a session migration concept, where the application managing UDP connections, so in that case, the QUIC protocol implementation, will get notification when a migration happens and can handle things correctly. For now, the QUIC sessions are opened only when the QUIC handshake completes, which means that packets have been exchanged in both directions. And so the UDP session is already pinned on the right thread, and we just open the QUIC session on the same thread. And that works fine, as long as there are no mobility events, because mobility events change the 5-tuple, so they can result in the connection conceptually migrating to a new thread. This will this will basically be a new UDP session for VPP, which will need to match to an existing QUIC connection. That's not yet supported, that will be soon, though. And then just a note on QUIC streams, the stream sessions will always be placed on the thread in which their connection lives. But now, the important questions.
Yes, how quick is it? So we did some benchmark, obviously, to see how well we were performing. And the issue is that for now, there is no canonical QUIC performance assessment tool. There are a bunch of tools being developed, but there is no canonical one. So what we did is develop a custom Hyperfly client and server tool that consumes the VPP message queue through shared memory, so attached to the application. And the basic setup is the client opens n connections. On each of those connections, it opens n streams, and then sends a certain amount of bytes on each and every one of those streams. And once the data has been received, a close notification is sent back on the streams, and when everything is closed in a connection, a closed connection event is sent, and everything should turn down nicely. So that allows us to test correction, but also speed. The setup we've been playing with consists of two different machines connected back to back with a 40 gig link, XL710. In each one there is a VPP running and the test application attached to it. So we do pin the calls, run VPP and the test app on the same NUMA, and use 15K bytes MTU. Those are 3.2 gigs CPUs. And the first results we're getting is that for one worker, so that was the first benchmark we did, for 10 connection and 10 stream on each, so 100 streams, we're getting approximately 3.5 gigabit per second for one worker. We're seeing that this scales quite linearly with the number of workers in queues. So we're getting up to 14 gigabits per second on 4 workers. We didn't do much more exploration there. But we're seeing some type of scaling. We did some testing with growing up to 100K streams per core, doing variations in the terms of connection, streams per connection. And the handshake rate is about 1,500 connection per second, limited by the message queue and the connect interface mostly. But that wasn't very satisfying at first. We said to ourselves, maybe we could improve that. And that because there were a bunch of issues and things that we could improve in our implementation. At first, Quickly uses internally a lib called PicoTLS, which is also developed by the same team at Fastly, to do the TLS handshake and the packet encryption and decryption. And as the API for this is pluggable, and as VPP supports now a native crypto API, we tried to use the VPP crypto API inside of Quickly in order to yield better results. And we also tried to do some batching of the crypto operations in order to improve speed. That proved to be working a bit. So basically what we do is instead of receiving one packet, decrypting it, and forwarding it, we do stack n packets, decrypt them at the same time, and then pass them to the protocol processing linearly. So basically the same idea as VPP is doing. The V in VPP stands for vector, vector packet processing, and we basically build vectors inside of this session layer. And we apply the same ID to the TX path. And that proved also to improve performance. And the last thing that we've been working on is the congestion control. The default one is Reno, which isn't really playing well with high throughput. We tweaked it a bit by changing the beta factor because we didn't have time to implement newer ones. But fortunately, it's also pluggable, so we'll be able to extend it in the future. And the results we're getting with this is an improvement of 30%, approximately, going up to 4.5 gigabit per second on one worker with the batching and the native crypto. And we're seeing that most of the cycles are spent in the CPU doing in the crypto part. And we hope that will accelerate with newer instruction in Intel Ice Lake CPUs. Yes. So to the future.
Yeah. So what's next? Of course, as you've seen, this is still a work in progress. There's still some work to do on performance optimization. One thing we want to work on is hardware offloads, because the crypto batching that Nathan just mentioned actually uses the quickly offload API, meaning that we process it. Currently we process it with VPP's crypto API in batches, but it will be also possible to send the packets to a crypto card for further processing and to free CPU resources. We want to support mobility. We'll have continuous performance benchmarking available soon publicly on the CSIT platform, which is the generic VPP continuous performance benchmarking. And of course, all of this is open source, so if you want to try it out or get involved, feel free to check out the code. The use cases for this QUIC stack now, because we don't do this just for fun, although it is fun, are of course HTTP3 servers, probably the most common use case for QUIC, but also gRPC over QUIC. gRPC can optionally use QUIC transport, and it's really well suited because of the built-in multiplexing. And there are also more network-oriented use cases like QUIC VPNs, which is similar to SSL VPN but better because it supports mobility, and using one stream per flow allows to get rid of the head-of-line blocking in case of packet loss in an SSL VPN. And also it's not harder to deploy because you just need a certificate for your server and an authentication mechanism for your clients. A funny trick we were experimenting with for the QUIC VPNs was to transparently terminate the TCP connections at the VPN gateway, meaning that the VPN gateway will actually hijack the connection and only send the TCP payloads, the TCP data stream, into the QUIC stream instead of encapsulating the entire packet. This has a nice property of getting rid of the nested congestion control issues, but we are getting also into dangerous middle box territory here. Now for the main takeaways of this project. So first, we really want to thank the QUICly guys because we had a great experience with their library. It proved to be easy to use, pluggable, very, very flexible. So I highly recommend it if you want to play with QUIC. We also now have an easy-to-use socket-like API for QUIC in VPP. And the VPP host stack proved to be extensible enough for new protocols which don't have really the same concepts as the existing ones, which was nice. And using the VPP framework also allowed us to quite easily get a good performance boost for QUIC. So we got a 30% performance improvement just by using the native crypto and the vector processing concept to our QUIC implementation. But of course, there's still a bit more work required there to reach max level of performance. We are a bit slower than TLS can be yet, but we hope we can reach similar levels of performance in the future. Thank you very much for listening. You have any questions?
You said you had a great experience with QUIC. Is there some other libraries similar to QUIC?
So the question was whether there are other libraries similar to QUIC. Yes, there are quite a few QUIC implementations open source on GitHub. There is in particular ng TCP2, which is the Nginx implementation. There is the Chromium implementation, which is implementing Google QUIC, which is a slightly different protocol from the IETF QUIC, which is currently being standardized. There are quite a few others, but we found out that most of them either were not implemented in just C, which was a problem for an integration with VPP, or made some assumptions about what the network looked like, how they gathered packets and everything. So that's why we chose QUIC.
Another comparison, please. How do you compare QUIC VPN with WireGuard?
So the question was how QUIC VPN compares with WireGuard. I am not familiar enough with WireGuard to answer that question, I'm afraid.
Yeah.
Do you wanna? So do you know? Well, do you wanna specify what WireGuard is, or? Okay. Okay. So yeah.
So you said most of the time, CPU time is spent in the crypto code.
Yes.
So what is the added value that VPP brings in terms of performance? In other words, what is the performance without VPP?
Right. So the question was that given that most of the time is spent in the crypto code, what is the performance benefit gain from using VPP? So it's quite simple actually. VPP has a really efficient crypto API, which compared to the default Pico TLS OpenSSL layers, gave us a big performance boost by minimizing copies, increasing the batching abilities, increasing cache efficiency, and everything. So that's mostly it.
So the performance gain is only due to the crypto optimization, or mostly?
Mostly, yes. Also as well to the stack, which is a bit faster in VPP than in Linux, but mostly. Yes.
Does QUIC have any concept like Linux TCP small queues? Because you've got a lot of data all the way between the application and the network card, and you can build up huge latencies. And having an end-to-end, end-to-end in the stack rate control would really help.
Great point. I think it's up to us. Well, sorry. So for the viewers on the camera, the question was whether QUIC has a concept similar to the kernel small queues to limit end-to-end latency. And I think it would be up to us to implement that now. But that's a great point.
Sure. For us, no.
Because unless you measure latency, everybody tends to measure bandwidth and get
Right.
great numbers, and then they get the buffer bloat.
Yeah. So in order to limit buffer bloat, we need to limit, to explicitly limit the FIFO sizes or the size used in the FIFOs at least. But yes, thank you. Yes.
On which card did you try your measurement? Because where I exist, I'm aware of number of vendors which provides hardware offload TLS and hardware offload crypto engine inside the NX. So I assume if you will use these cards, you will get better performance.
Yes. So the question was whether which cards we used for the testing and whether we used cards that had physical, offload properties for QUIC. We used Intel XL710 cards for the test. We know that these cards have some offload properties. We didn't use any. We focused only on software processing. Offloading is an interesting topic. There are some offloads that are possible inside the card or with dedicated devices further in the processing pipeline, meaning once the packet has been received, we can also offload the crypto, for instance. Both the inline offload, where the card does the processing and then passes the pre-processed packet to the stack, and the what we would call out-of-band offload, where we do some processing in software, then send the packets back to a card for crypto, which is the main point. So both these models exist. Both are interesting. We think the out-of-band is more flexible and easier to use, but the in-band may provide better performance.
Just one last question.
So you mentioned that you could only use the libraries which were written in C because you had to compile them the same way VPP is compiled, right? So is that true? Did I hear it correctly?
Well,
we said that, but it was not. So the question was, did we choose quickly because it was in C and that we needed that for compile with VPP, if I understood correctly? And the answer is it was a part of the criteria. It was not the main one, but easiness of compilation and interaction between VPP and quickly was a concern because of easiness of coding the.
it's not a hard requirement, but it makes lots of things simpler.
Okay, great.
Yeah.
Thank you.
Thank you.
Sorry. You can